So good afternoon, everyone. So welcome to the statistical shape modeling and analysis using image data. And we have three speakers, and you are encouraged to turn on your video. So in that case, so the speakers can see you and just want to make us have more interactions. So, and I'm the chair of this section. My name is Chao Huang from the Florida State University. And so let's start. So the first speaker is Sebastian Kurtek from the Ohio State University. And the title of his presentation is Visualization and Outlier Detection for Shape Data. So Sebastian, you can start.
Thank you, Chao. And thank you all for being here. Before I start, I should mention that this is work jointly with a former graduate student of mine, Wei Shi, and also a colleague in statistics here at Ohio State, Oksana Shkrepty. Okay. Oh, all right. So just to sort of convince you about the motivation behind this work, curve data and in particular shape data are the primary objects of interest for data analysis in many imaging applications. And so here I'm just showing a few. They range from computer vision and bioinformatics to sort of applications in biometrics and medical imaging. And really an important application of this work is in fact in medical imaging, where we're often interested in visualizing variability in different types of structures. And so here at the bottom, I'm showing some 2D slices of a brain tumor. The brain tumor is highlighted in red. And one important question in this application is to assess the shape heterogeneity of the tumors and try to relate that information to, for example, survival. And so effective visualization techniques can actually help us in assessing tumor shape heterogeneity. Really, the broader motivation was to design a visualization toolbox to essentially be able to assess variability in shape and more generally actually functional data and use it in exploratory data analysis. As we all know, effective visualization tools are also really important when we try to communicate results of statistical analyses to experts in applied fields. And so the hope is that such a toolbox can help in that process as well. So in this research, we developed a framework for visualizing different sources of variability in curve data. And so here I just have a list of these and I'll clarify what each of these is in a minute. But when we're given curve data, the raw data itself contains variability in shape, variability in scale, variability in translation, rotation, and finally parametrization. If we think about curve data in terms of these different components, we can also develop a framework that will allow us to detect outliers of different types that are related to each of these different sources of variability. And so to achieve these goals, as you'll see on later slides, we'll work in the squared velocity function-based elastic shape analysis framework. So that will be sort of the vehicle that will drive the development of the methods. What is the main challenge here? Well, as you'll realize in a minute, many of the sort of relevant representation spaces, for example, the shape space, are non-Euclidean and high dimensional, and so this poses challenges in developing visualization techniques. So here is sort of a very busy picture, but this is the idea. The idea is to take some original data. In this case, they're just shapes of butterflies. And as you can see, if we just look at the original data, there's not much information that we can extract right away. And so instead of looking at this picture right at the beginning, what we'll try to do is we'll try to extract these different sources of variability that I just described on the previous slide. and then construct visualizations for each one separately. And the hope is that we can extract more information from these individual visualizations. We'll construct what I'm calling box plots. They're box plot type displays. And so you'll see how these are constructed in a minute. Okay, so before I start with that, let me just introduce a little bit of background information that will help with understanding the rest of the methodology. So I'm going to use beta to denote a parameterized curve. This curve has some domain D, so for closed curves, it's a unit circle. For open curves, it's just 0, 1. The curve can take values in RD, so you know, these 2D curves where D is 2, or 3D curves where it's 3. To define reparameterizations, we use this group gamma, and these are essentially nice smooth mappings from D2 itself. And so then for a particular reparameterization gamma, if we take the curve beta and compose it with that gamma, this results in a reparameterized curve. Now, the key point behind this is that a reparameterization of a curve does not actually change its shape. And so this is a source of variability that in a lot of applications of shape analysis is a nuisance. So we have to remove it from the representation space. Now, under the elastic functional shape analysis paradigm, we work with the squared velocity function, which is a transformation of the original curves. And this is given here, and I'm denoting it by Q. So essentially, this transformation just depends on derivatives of beta, and it depends on this derivative in this way. Okay, so what are some properties of the framework? Because the squared velocity function Q only depends on the derivative of beta, then translation is automatically removed. So we don't have to worry about the translation variability. If we rescale all of the curves in our data to unit length, that takes care of scale variability. So we normalize the length of all the curves. And then some other important properties are that under this squared velocity function representation, the L2 metric that we'll use to perform all of our analysis is invariant to reparameterizations. And so this will allow us to remove parameterization variability as well. And then finally, maybe as a side note, I view this as a very useful property of the framework, is that this L2 metric on the space of SRVFs actually corresponds to what's called an elastic metric on the space of curves. And this gives us some interpretability of the types of deformations between shapes that we'll extract. Okay, so going a step further, if we remove scale, as I mentioned on the previous slide, the space of squared velocity functions becomes a sphere. If we rotate a curve beta using a rotation matrix O, its SRVF changes in the same exact way, so it's just a rotation of the SRVF. But if we reparameterize a curve beta using a gamma, so if we take beta composed with gamma, its SRVF changes in a slightly different way, where we have also a composition of the SRVF with gamma, and then this extra factor of the square root of the derivative of gamma. We can put essentially all of the curves that vary just in rotation and reparameterization into what's called an equivalence class, and then this equivalence class will represent a shape uniquely. So essentially, you can think of this equivalence class as just the collection of the same curve, but rotated and reparameterized in many different ways. And so the method that for constructing these displays will be distance-based. So the shape distance that we define that's given here is a distance between equivalence classes where we minimize over reparameterizations and rotations. And then this is just the distance between two SRVFs on the unit sphere. One benefit of working under the elastic framework, where we have to sort of worry about this invariance to reparameterization, is that in general, elastic deformations between shapes at least to our eye, appear more natural than if we did not account for the parameterization variability. And so this is one benefit, especially if we're trying to design different types of displays for shape data. Okay, so how do we actually go about extracting all of these different sources of variability? Really, the hardest one is the shape variability, and this is what I was building up to. So before we even start, we first extract the translation and scale components, and again, I already described this in briefly. So the translation component corresponds to the centroid of the curve, and the length of the given curves is the scale component. Once we do this, we can compute what's called what I'm calling here the shape median, which essentially is the minimizer of the sums of distances from all of the data observations in our data. And so the result of this optimization is the shape median, which here I'm calling Q bar. It's just, as we select a single element of this entire equivalence class for the display. We can also compute all distances of our data from the shape median. So these are denoting by ds1 to dsn. We can extract the orientation component. So when we compute this shape distance of the data to the median, we have to go through this alignment procedure, right? So we have to rotate the data so that it aligns with the median, and we have to reparameterize the data so that it aligns with the median. And so these are what I'm calling the orientation component or rotation component, and then the parameterization component. Finally, the shape component is defined as the data where I've applied this optimal reparameterization, this optimal rotation. Okay, so here's just another picture to show you the idea. I'm given data that's shown here in the left part of the slide. The parameterization component in general is hard to visualize on the original data. So here I've just marked a few points in different colors to show you that the parameterizations can be very different. So these colored points actually correspond to each other across the different curves. And then in the bottom, I'm showing you the different components that were extracted from the data. So in panel A is the translation component. In panel B is just a standard box plot of the scales. Panel C contains the shape component. Panel D contains the orientation component. And then the parameterization component, here I'm splitting into two parts where in panel F, I'm showing you sort of the best starting point on each of the curves. And then in panel E, I'm giving you the reparameterizations given that starting point. So I've actually split it up into two further components. Okay, so I'm going to describe sort of in words how to construct what I'm calling the shape box plot. And then I'll tell you how to construct similar types of box plots for the other sources of variability. So to start, we'll keep 50% of the shape data that's nearest to the shape median. So we can do that just by ranking the distances that we computed as part of computing the shape median. We will take all of the shapes in our data and we'll project them into the linear tangent space of the shape median. So we'll locally linearize the shape space. And then in this linear space, we'll find quartiles by optimizing an energy that essentially depends on two terms. The first term captures separation of the quartiles according to the distance from the shape median. And essentially we want the quartiles to be far away from each other. And then the second term captures the direction of the quartile vectors. So we don't want to pick essentially two of the quartiles that point in the same direction. We want them to also somehow capture the variability in this tangent space. There's flexibility in how this is done. So the two terms are weighted and one can tune the weight depending on the application. Once we do this, we define the interquartile range as the shape distance between the quartiles, but this distance is computed as we pass through the median. So we go from quartile 1 to the median, then to quartile 3. And the distance that we travel is what we call the interquartile range. As I mentioned before, we're interested in detecting different types of outliers. So to detect shape outliers, we'll essentially take our 2 quartiles that we computed, and then we'll add some constant k that's multiplied by the interquartile range, that's also then multiplied by the direction in which the quartile is pointing. And so this essentially allows us to isolate a region beyond which the data that we have will be called outliers. This constant k, right? I mean, we've seen these formulas before. This constant k, though, in the case of the shape space and some of the other more complicated spaces, it's hard to fix it fix it for essentially all applications. And so we've used a lot of simulations to actually tune this constant to provide some general guidelines for detecting mild, regular, and severe shape outliers. So again, there's some flexibility in flagging observations as outliers. And so finally, we define the shape outliers as those that are further from the shape median than the shape outlier cutoffs. And sort of to complete the picture, the shape extremes, so things that correspond to the minimum and maximum in some sense, will be the 2 shapes that are closest to each of the 2 outlier cutoffs, such that they lie outside of the 50% central shape region and are not flagged as outliers. Okay, so I said a lot, but here's sort of the result of this procedure. So here in A, I'm just showing the shape component in a slightly different way. The shape component is the same as what I showed in one of the previous slides. In B, I'm showing this, what I'm calling the shape box plot, where you sort of have the median here in black, the 2 quartiles, the 2 shape extremes. And one thing that can be done here, and it's sort of subtle in this picture, is that the spacing between the shapes in this display can be according to the distance between the successive shapes in the box plot. So that way you can sort of capture how much variability there is in the different directions. And then at the bottom here in C, I'm just showing the shape outlier cutoffs. So things that are more extreme in some sense as these types of shapes will be flagged as outliers. And there were no outliers in this data. Okay, so I'm quickly running out of time, but let me just tell you a little bit about the other sources of variability. For the translation, we again use a similar procedure as to the shape box plot. For scale, we just use the standard box plot. For orientation in 2D, right, the rotation matrices we extract are elements of SO2, and SO2 can be identified with S1. So essentially, it's like constructing a box plot on a unit circle. And so we use that to our advantage. If we have data in 3D, we use, again, a similar idea to the shape box plot, but now based on the geometry of SO3. And then, again, we use the geometry of gamma, the group of reparameterizations, to construct box plots for that source of variability. And so let me just show you a few examples, and maybe I just have time to go through the first one, and I'll skip the second one. So this is essentially a simulated example where we have these different 3D spirals, and essentially they vary in sort of the width of the spiral and then the length of that straight segment at the bottom. So here you have the different sources of variability that were extracted. Here I'm showing the rotation as a rotation of essentially the standard frame in R3. So you can see that in the original picture, there's a lot of variability, and it's hard to see much just based on that. And so here's the shape box plot. So again, I've separated spirals according to the distance between the successive curves. So we sort of see that variability ranges from sort of thin spirals with a long straight segment to things that are sort of thicker spirals with a short segment. And then we found some mild shape outliers where sort of that straight segment is very long and the spiral is very thin. Here are the other box plots. This is the translation box plot. In this case, translation is not very important. In some other data scenarios, translation might be important, and so we would want to look at this. Here's the parameterization box plot. So again, we see sort of variation where we go faster and then slower along the curve versus slower and then faster. And so again, intuitive given the data that we have. And then finally, we have the orientation box plot, and again, we flagged a couple mild orientation outliers. Here's an example for some handwritten text. And so again, I'm not going to really focus on this top part, but we can construct these different box plots here. Here's the circular box plot I described for rotations in 2D. So essentially, we just identified with the angle in a circle, and then we can nicely see the variation in rotation of the different curves. Here we flag two outliers in rotation, some outliers in translation, and then in the bottom you can see the shape box plot again, where sort of the variation is quite natural, right? In this first letter here, we see that this loop sort of expands, this loop contracts, and then there are some other deformations in the other letters. Okay, so I've run out of time, I think, so I'm not gonna tell you again what we've done. I'm just gonna skip this and just thank you again for giving me the opportunity to speak. Here are some references. The main reference is this paper at the top, and I guess there will be a time for discussion at the end of the session. Thank you.
Thank you, Chao, for the introduction. It's good to see old friends here. So today I'm going to talk about surface-based connectivity integration. And from the title, you can tell that I'm interested in brain connectivity and the connectivities on the surface, and I'm interested in not only one type of connectivity, multiple types, because the integration here. So I'll start with the introduction here. Broadly speaking, there are two types of analysis in brain imaging world: surface-based analysis and volume-based analysis. Like the software Free Surface promoting the surface-based analysis, and other software like FSL and so on promoting volume-based analysis. Excuse me. Both of them have advantages and disadvantages. In this talk, I'm going to try to mainly motivate, promote the surface-based analysis. From the title, you can tell. So why? I'm going to give you a few reasons for that. Before that, here I list a few milestones for the surface-based analysis of brain imaging data. From 1990, basically 2 decades ago. Two papers was published in neuroimaging, and that just marks the birth of Free Surface, which is a piece of classical software that we're currently still using to analyze brain imaging data. And from then, surface-based analysis became very popular. For example, Dr. Van Essen, the PI of Human Connectome Project, published a few papers in 2005 and so on to follow up with the surface-based analysis, and also this surface-based analysis is promoted by the Human Connectome Project. And then even recently, from the group Paul Thompson and I think Bruce Fisher, he moved to UC San Diego, and his group also published alignment methods for analyzing data on the surface and so on. So this is a continuing and ongoing research on the surface. And why, analyzing the data on the surface of the human brain instead of the volume data? The first impression, maybe the volume is the best representation, because that's what you got from the scanner, right? But however, here I would argue that surface is actually the best representation of the data. First, the cerebral cortex has topologic of 2D sheet. If you think about the brain, the gray matter is the most important. It's one of the most important component in our brain, and basically it's 2D sheet folded inside the skull. And many features, for example, the cortical thickness and so on, can only be well measured on the surface. You have basically two surfaces that you can extract from the brain. One is called pile surfaces, which is outside the gray matter, and another one is called white surface, which is in between the white matter and the gray matter. So the white surface is more rough compared with the pile surface, and the white surface is going to be what we use today for our analysis. So the second reason for using surface-based analysis is the alignment is easy. Think about that, the most difficult part for statistical analysis of imaging data is to find alignment. And it's pretty challenging for doing this in 3D, but it's relatively easy for this alignment on the surface, which is a 2D space, at one-dimensional less than the 3D. Another important advantage for doing this type of analysis on the surface is that when you do the alignment, when you try to find correspondence between people, you don't really need to change the shape of this surface, this pile surface or white surface. You only need to change the parametrization of the surface. Basically, you just try to derive some diffeomorphisms of the spheres and apply them to the surface. And the grade on the surface changes, but the shape does not change, which to me is very natural, but this cannot be done in 3D. And in 3D, if you want to do the alignment, you have to deform the actual shape of the brain. Also, analysis is much easier. And here you have a nice domain, which is a spherical domain. And if you can project the data, so we're developing frameworks for projecting all sorts of data, including the diffusion matrix like FAMD and so on, and PAT measurements and cortical thickness and other kind of topological measurements all onto the surface. And once you have that, including the connectivity and so on the same domain, you can kind of develop standardized algorithms for statistical analysis. In general, people would be interested in group-wise comparison or regression type analysis and so on, or embeddings, dimension reductions. And once you have the data and the data represented in a standard domain, in a standard format, so you only need to develop one algorithm, one statistical procedures, and then that can be applied to all sorts of modalities of images and so on. I think that's pretty cool. So okay, let's shift it to the topic of connectivity. So in this talk, I'm interested in two types of connectivities. One is functional connectivity, and another one is structural connectivity. Functional connectivity has been well studied on the surface because the Human Connectome Project pipeline actually promotes the study of functional connectivity on the surface. And they even develop a format called GIFTY format to store the data on the surface. However, structural connectivity is pretty rarely studied on the surface. So there are many reasons for this. First, current diffusion imaging data is it's low resolution, and the measurements of the diffusion signal near the white matter and gray matter interface is not very reliable. There are many reasons for that. I'm going to explain a little bit. And also streamlines, which come from the tractography algorithm, also often stop in the white matter without reaching the gray matter. So it does not really reach to the surface, and there's no way you can build connectivity from this white matter or streamlines because of this. And also you often got a biased connectivity because of the gyro bias in tractography. When we say gyro bias, the brain are folding, so you have a lot of peaks and valleys and so on. So this is one illustration of the gyro blend, where the actual measurements encourage you to directly build streamlines to the top of this gyro blender. and then you actually ignore the wall of this gyro. And this causes a lot of bias. So basically, when you build the connectivities on the surface, you only cover the peak and you kind of ignore the wall. That's not truth. It's not the truth. Because from histological study, people find that there's all sorts of fibers connecting to the wall of this gyro blender. Okay, so that is fundamental problem preventing us from using the surface to study structure connectivity. And another challenge is that computational challenge. I think it's, this morning, Annie just talked about it, some correlation, decomposition, and so on, if you were in her talk. And here we also have the same challenge. So on the surface, think about the resolution of the surface. If you have 10,000 vertices to represent your surface, then you're probably going to want to reconstruct 10,000 times 10,000 kind of connectivity matrices. And in order to be not so sparse for your connectivity matrix, you have to build hundreds of millions of fibers. That's, like one subject, you have to build like 1 terabyte data in terms of streamlines to get a reliable estimation of the connectivity, which is not computationally feasible. So there are many challenges for doing that. So that's why this method is not still very popular. And one of our goals is to overcome those challenges and so on, to develop a pipeline to solve those problems and to build an infrastructure. So to solve the connectivity bias problem, I think people just realize that and then start to work on methodologies to solve this problem. And Max's group have this surface enhanced tractography. And basically they try to incorporate geometric structures from the surface to build streamlines. So at the interface region, they just use the surface flow technique to build a price from the geometry of the white surface. Because there the signal you measure from your scanner is not so reliable. So instead of using the signal you measured here, they propose to use some prior knowledge that summarized from historical data, right? So that's that overcome this gyro bias and get more uniformly distributed connectomes on the surface. Another kind of recent work by Katter et al. Recently published in neuroimaging used vector field-based tractography algorithm. So they model the fiber curves in the gyro blender as a divergence-free vector field. And this is the constraint they imposed to this vector field. And then under this constraint, they have some kind of representation of this vector field in terms of linear combination of basis and coefficient. And then they build an objective function to obtain this vector field. And this objective function contains multiple terms, from prior knowledge of the cortical thickness. They believe that if your cortical thickness is thicker, then you're going to have more fiber curves there. And the radial information, so they believe the fiber curves should touch the surface perpendicularly instead of parallelly or some angle. And you also have information from the data you measured from the scanner and also some roughness penalty of this vector field. And we also kind of working on this. So our work is taken from a different angle where we try to incorporate prior knowledges from the historical data. We have a lot of high resolution historical data. Can we somehow, and human brains are very similar, can we summarize those histological data and then inject those priors into new subjects that we're estimating and so on? Especially, if the data you're working with is not so high resolution, then you're gonna need some kind of this prior to help you to regularize the signals or the FODF field you estimate. So we kind of reconstruct, do something under the kind of Bayesian idea that we also construct some objective function that combine the data and the historical data and some geometric prior that you can extract it from the surfaces and so on, and to estimate diffusion vector field. So in this region, basically, You can see that's a comparison of our methods and existing methods. We haven't finished it yet, but with very few number of factors, we can reconstruct the FODF pretty well, and then the streamlines and connectivity pretty well. So that is kind of the engine behind this surface-based connected integration pipeline we developed. So this is the kind of flow chart of the pipeline we're developing. So from the DICOM data that dump out from the scanner, you can use our pipeline to do the analysis. And the pipeline takes three image modalities: diffusion, T1, and resting state, and then do pre-processing, surface projection, reconstruction, and so on, and all the way to tractography and FC cleaning and so on. And then you can get a continuous SC and FC on the surface. This is just showing you one example of a connection to a seed point. And then we have to do some kind of surface alignment to build everyone, bring everyone to the same space to establish correspondence between people, because different people have different shapes of brain surface and so on. And then you can start to do connectivity integration, and because everyone now in the same domain. So, you know, whatever kind of analysis you want to do here, you can also do in this things kind of align in the domain. Some keywords here is that we promote continuous connectivity, which I think is fundamentally different from the current brain connectivity people are studying. And here we have a functional data instead of discrete matrices. And we have, you know, coupling, and I will give you some examples. And we also try to do some connectivity alignment. That's alignment between subjects using the connectivity information. So this is the continuous functional connectivity idea. So what we do is here we use omega to represent the domain that we're interested in. Actually is the union of two white surfaces, or you can consider it as the union of two spheres, because topologically they're isomorphic to each other. And we define the connectivity as a continuous function on the domain of omega cross omega, because connectivity you have like, you consider the relationship between 2 points on this omega, right? So, and essentially, you got a functional connectivity. This is the set of all functional connectivities, which is the mapping from omega cross omega to -1 and 1. Depending on how you define the connectivity, this range can change. And then we also have symmetry constraints, because X, Y, and Y, X can have the same connectivity. And we let the diagonal equal 0 because we don't really care about the self-connection. It can be equal 1 as well. And similarly, we can define the continuous structure connectivity from the tractography algorithm we introduced, right? Once you have those ending points on the surface, and this whole process is just like a point process on the domain of omega cross omega, and you can estimate the mean function from this point process. Or another way that you can treat this as a probability, the connectivity as a probability density function. That's what we do. We believe that this we have this additional constraint that the integral of this structure connectivity equal to 1. So basically, what you get is a probability from X to Y. If you have two regions, you can see the probability of two regions get connected. I'll define the connectivity in a moment. I don't think I have much time left. I will go faster. So in order to get this continuous connectivity, you have to do some kind of smoothing technique. Here we use kernel density estimation, but there's no kernel defined on this complex domain, which is omega cross omega. So we have to build our own kernels, and the kernels is defined from like a heat kernel on a two sphere with some slight modification. And then, you know, with this continuous functional, continuous structure connectivity defined on the surface, and then we can start to define the coupling. The coupling actually means the similarity between the functional and structure connectivity at any point of the surface. So we can define global coupling that basically compare the connectivity to a particular point x0 to the rest of the brain, and we use inner product to define the similarity. This is similar to the correlation of this function and structure connectivity. And we also can define local coupling. Basically restrict your connectivity to a local region, and this still give you a continuous function on the sphere. And we also can define discrete oscillation-based functional connectivity and structure connectivity and the coupling by some integration and some correlation calculation. So we're using the Human Connectome project data to do some kind of validation study. So we have done pre-processed 900 plus subjects, but I think the result I presented is only based on like about 100 subjects. The pipeline we developed is pretty time consuming because we get high resolution DTI data, we get surfaces and so on, high resolution functional connectivity and structure connectivity. So it takes about like 7 days for one subject. So that's the very beginning, we didn't process so many data. I'll skip some EDA. So there's one interesting figure I want to show you is that the distribution of the functional connectivity with and without a structure connection. So in statistical literature, people usually tend to model, try to incorporate structure connectivity into their model when they try to estimate functional connectivity, with the assumption that once you have structure connectivity, you're going to have a higher functional connectivity. So that is like kind of also most of the time it's kind of intuitive, but no one has really shown some figures of that. After some figures shown before, but here we reproduce this result and demonstrate that functional connectivity with structure connection actually is usually has a higher value, higher mean value. So we can see that there's two histogram of functional connectivity with and without structure connections. And we also done some reproducibility study. The continuous coupling usually performs much better in terms of reproducibility compared with the discrete coupling. And in existing literature, people usually, most of the time, I think 99% of the time, people use discrete the coupling to study the topic they're interested in. But here, I want to say that using continuous is much more reproducible and much more informative, actually, in the table I'm going to show in a minute. This is just basically give you some idea about the coupling, the mean coupling in males and females. This first two rows are the females, second two rows are males. And we're interested to test the difference between males and the females. This is the binary mask you eventually got, which contains a significant difference regions between the males and females. So they mainly focus on the sematosensory motor area, and some of them has like the front lobe regions. So sample size is relatively small in this case, so we don't really put much effort to interpret the results. This should be redone in using more data. And also the classification study is more interesting. So we show that we try to classify males from females using the high resolution SCFC coupling. And the continuous SFC give much better results compared with the discrete ones, and with the traditional ones that this discrete one is obtained from our high resolution connectivity. But traditionally, if you use those pipelines like the PSC and so on we developed before, and you get a really bad results. So indicating that you shouldn't really use that connectivity at this cost scale to study the interaction between SC and FC. In terms of implementation, we kind of built a GitHub website and to host our pipelines over there. And now the pipeline is developed under Python and in the Anaconda environment, which is pretty reproducible. And we're also working on a Docker and Singularity version, where you eventually just download an image. You don't need to really configure your computational environment to reproduce our results. So I think that's pretty awesome. And based on this work, we'll try to do some kind of downstream analysis, including connectivity alignment. This is joint work with Anuj. I need to really work hard on this project. And we also try to analyze the continuous connectivity as functional data on spherical domain, develop methodology for factorization, decomposition, regression, and hypothesis testing, and so on. Because this is a new type of connectivity, I think, it's under the continuous framework. So another application we're trying to do is multi-scale network analysis, because from continuous to discrete is super easy under this framework. As long as you have passivation, you can define the discrete cases. And here we try to do something that invariant to the passivation that you imposed. Because, given one passivation, you get one result, given another passivation, you get another result, which is pretty arbitrary to us. So is there the way to develop something that invariant to the passivation that you're using, that to enhance the reproducibility and so on in the neuroimaging study? So that's all, and I want to acknowledge my collaborators and students. Madi and Carl contribute a lot to this project and some funding support. Thank you.
Our next speaker is Chao Huang from the Department of Statistics at Florida State University. And he will tell us about geodesic factor regression models with misaligned pre-shape responses in statistical shape analysis.
Okay, thank you for the introduction, Sebastian. And today I want to introduce some of my recent research work. And the title is Geodesic Factor Regression Model with Misaligned Pre-shape Response in Statistical Shape Analysis. And this work was just accepted by the 2021 CVPR as an invited oral presentation. And this is work we joint work with my colleagues Anuj and our new coming professor Rongji Liu. And this is outline of my talk. First, I will introduce some backgrounds, and then I will introduce the proposed regression model, geodesic factor regression model, and the estimation and inference procedures for this model will be discussed. And after that, and then some simulation studies and real data analysis will be included. Finally, some take-home message and future work will be discussed as well. So first, background. So as we know, recently a lot of large-scale biomedical studies comes out and with different kind of imaging modalities. So these days we have a lot of data sets and with different kind of medical imagings. And for all these medical imaging data, and we are interested in some objects from this medical imaging data. And for this, for example, like for the 2D objects, like the corpus callosum within our brain, and usually we are interested in maybe one size, like the sagittal view. And also for the mole in the skin cancer, people are interested in the shape and size of different geometric informations of these of these objects in this 2D image. And also we are interested in some 3D objects, for example, the hippocampal surface. And also if we have this knee MRI and we can extract this joint cartilage, and we are interested in the surface information of this cartilage because when people have this osteoarthritis issues and the cartilage thickness will be shrinked. And also, so in that case, the shape of all these objects extract from the medical imaging data is of great interest these days. And next, these days people are interested in this statistical shape analysis. One of the most important or popular shape space is the Kendall shape space, and which means that if we have this like the landmarks of 2D or 3D objects, And then we remove certain shape preserving transformations like the rotations, translations, and the scales. After that, the information left we can treat as the shape information. So in that case, so the shape representation space is usually shape representation space are usually nonlinear and high dimensional, which is also a quotient space geometry. For the last property, because as we introduced for this candle shape space, usually we remove all these shape preserving transformations. So in that case, the shape representation space are invariant to these shape preserving transformations. And different kind of statistic shape analysis tasks has been visited these years. For example, like the shape statistics, I think, and Sebastian and Zhengwu has talked a lot for these shape statistics, and also the hypothesis testing problem for the shape data, and also like unsupervised learning and supervised learning based on the shape information. And another very important topic in the statistical shape analysis is shape regression analysis. So the aim of shape regression analysis is to model the relationships between the shape response and some Euclidean queries of interest. And currently there are two main approaches in this shape regression analysis. One is, we call it extrinsic shape regression. And the key idea of this approach is, so first we can embed all these shape response into a high dimensional Euclidean space. And after that, in that Euclidean space, we can apply different kind of classical regression model. And after that, we can project back all these estimated models and predictions back to this original shape space. But however, there are some drawbacks. So first, if we do it, all the regression analysis on this embedding space, which means that we just lack in these preservations of all the local shape geometry. Second one, so the existence of this inverse and continuous embedding map to this shape space is not always guaranteed. And the second approach we call intrinsic shape regression, which is a natural generalization of this regression model from the Euclidean space to the shape geometries. And usually we need to use some tools in the differential geometry. So here I just quickly go through all some basic knowledges in this differential geometry. So here we use M as a d-dimensional and complete Riemannian manifold, and we call the TYM is a tangent space at a specific point Y that on this manifold. And we have this geodesic curve, which is defined from 0 to 1 to this Euclidean one-dimensional Euclidean space. And also, we can see that we can define the exponential map as Y is exactly, we call it EXPY, and it is a map from the tangent space to the manifold. And also we have this log map, which is also, we call it inverse exponential map, which just puts the point from the manifold back to this tangent space. And based on this log map, the definition of this log map, we can define the Riemannian distance, which is defined in this way. Okay, so this is, just want to give you guys a quick and go through all these preliminaries in the differential geometry. And now we can just talk about some details for this intrinsic shape regression. First, we have data sets. We have some predictors which come from the Euclidean space, and we have all these shape responses. For example, we can assume that they are in the candle shape space. And we can write down the geodesic regression or intrinsic shape regression model in this way. So here, the EXP is an exponential map we introduced in the previous slides. And now we have two important terms in this regression model. One is the kappa X, which we call as a conditional mean shape. And you will see that we can treat this one as a link function. It can be treated as a parametric setting. like we can just use as an exponential map from the base point mu and to the with some tangent space vectors like the b times xi, and then we can get a new point, which is we call the conditional mean shape. And then the second important term in this regression model is error term. The error term is usually defined from the tangent space, the t kappa xis. And also it can be defined in different ways. For example, it can be defined in the parametric model, like the Gaussian distribution on this tangent space. Also, we can use some semi-parametric model. We can give some conditions on the first and second moment of this epsilon. And also we can use some non-parametric model here. And there is one important issue in this model is, so as we know that usually what we have or we can extract from the medical imaging data is like the nanomarks or the coordinate information of all these nanomarks along the contour for these 2D objects. So which means that, so this information, what we can do is we can only remove the translation or scale, and then we can post this nanomark information onto a pre-shape space onto the rotation group. And then we can use a quotient. In that case, we need to use a quotient space geometry to specify these regression models. And in practice, usually we use some pre-processing steps, which means we can just remove these rotation group actions with a tangent, with a template over there. And in that case, we can guess, we call it shape information after we do these pre-processings. But there are some issues in these pre-processing steps. As we know, usually we need to have this template, which means that if C is the template, and then we do all these alignments from A to C and also from B to C. We can guarantee that under some specific objective functions, and A to C can be well registered and B to C can be well registered. But nobody can guarantee about the alignment between A and B, right? And because of these issues in these pre-processing steps, there are some limitations in the intrinsic shape regression model. So first, we know that as we can use different kind of this registration method, no matter it's the traditional ones or machine learning based or deep learning based, we usually have these misalignment issues in these pre-aligned registrations, just as the picture showed here. As we already done a different kind of, we already done this kind of alignments, we still can see that there are strong misalignment issues over there. And the second, so this kind of alignment sometimes is not optimal. So what does it mean? It means that this kind of alignment sometimes is related to the imaging heterogeneity. Like, for example, we have two different groups. One is normal control, another is the disease patients. And maybe for these two, this kind of alignments is highly related to this group information, which means that we may need to use different template for these two different groups for this alignment. But if we just use some traditional way to do this kind of alignments, which means we use one template and to do these alignments, which means we only use this image information without any queries or with any clinical variables into these registration procedures. So this is not optimal here. So our goal is that maybe in some certain sense, we can do all these alignments using both this imaging data and the predictors or the clinical variables. And the last limitation is sometimes for all these existing intrinsic shape regressions, they don't spend too much investigations in this spatial correlation structure establishments. So one of our aim in our proposed model is we want to use some specific structures to build up these spatial correlations for this local geometry. And now we want to introduce the GeoFarm, the geodesic factor regression model. So first we want to introduce the pre-shape space for the planar curves. So first, this kind of, we use S2K and to indicate the pre-shape space. and which means that the pre-ship space is, if we have all this landmark information, we remove this translation and we remove the scanning information. After that, we can get the information which we call this information is on this pre-ship space. Okay, and as we know that there exists a map which can connect this pre-ship space and the hypersphere space. So here we call this kind of function is f, and we know that with this f function, then the pre-ship space is equivalent to this hypersphere space. And now we just move all these problems onto this hypersphere space, and so we can as we know that all these exponential map, log map, and parallel transport has been already defined for this hypersphere. So now we want to introduce the geodesic factor regression model. So we can introduce here the Fy. Here the GI is a rotation group action. So here, instead of put this kind of rotation group action onto this pre-ship, we put this kind of rotation action onto this the yi here. So in that case, and given the xi and the zi, the Fyi star gi follow this Riemannian normal distribution. And here, as we introduced for this intrinsic regression model, the conditional mean shape here, we can use this exponential map with two different terms. One is a base point, which is f mu. Another is all this information on this tangent space. We have two parts. One is b times xi. The b is xi is all these observed predictors, including demographic information and clinical information. And b is the tangent vectors, which represent all the effects from the predictors. And the lambda and zi here is the latent variables, or we can call it as the latent factors. And the lambda here is all these the loading matrix related to all these latent variables. And we can see that this model can be used to build up the relationship between the pre-ship response and the Euclidean queries of interest, of course. And also you will see that in this model, we introduce the GI, which is the rotation group action. This kind of rotation group action can be used to detect all these individual nuisance transformation. And also we use this kind of specific parametric structures for the conditional mean shape. And here, this is for the Riemannian normal distribution, we use isotropic Riemannian normal distribution. The probability density function is given in this way. And you will see that, so here, it's similar to the factor analysis model in the Euclidean space. We build up a similar model on this pre-ship space. And this factor analysis model includes two parts. One is the latent factor represented by the lambda. So each vector you can see is defined on this tangent space. It can be treated as these latent factors. And also we have this kind of stochastic error terms epsilon I, which following this isotropic Riemannian normal distribution. And here are some advantages of our GeoFarm model. So first, this model is the first one can deal with its misalignment issues in the pre-aligned response. And second, and you will see that when we estimate this whole model, the GI can be learned not only from this imaging data or from the ship data Y, we can also learn from these the predictors, the clinical variables, and the demographic informations. And the second, the next advantage here is we use we call it the Riemannian and factor analysis model to build up these variabilities among the pre-ships. and we can just capture all these local geometries between different pre-shapes. Okay, and one of the advantage is the computational advantage, because when we just put this GI, this rotation group actions on the Y, actually the GI can be represented by the two-dimensional orthogonal matrix, which means that we don't need to estimate the rotation, the high-dimensional rotational group. We only need to estimate the angle within this orthogonal matrix, which is only one-dimensional. So it's very easy to estimate these parameters, the nuisance parameter here. So here we have this. I think I really like this picture. I think it can just tell you all the important terms for our geodesic factor regression model. You will see that. So we can just see how this data generated from this geodesic factor regression model. First, we have this base point f mu, which is on the hypersphere space, and we have this kind of all these demographic information or clinical information with the corresponding effects on the tangent space. We also have some latent variables and with this loading matrix on the tangent space. And then we can just do this exponential map, go to another point on these manifolds. But because we have this kind of rotation and nuisance rotation and factor actions, so in that case, we already have this kind of another move from one point FYI to another point is FYI star GI. So this is looks like the nuisance parameters here. So you will see that. So this is how this data generated from this geodesic factor regression model. And now we just go to the estimation and inference procedures. So the key aim in this estimation procedure, we need to get the maximum likelihood estimation of all the three different parts. One is the parameters of interest, including the base point, all these tangent vectors related to the predictors, and also the loading matrix for the factor model. And also we need to estimate the nuisance parameters, the sigma, and the nuisance transformation, all the individual rotation rotation actions. And we can treat this estimation procedure as this complete log likelihood function-based optimization problem. Since we have this latent vector, which is missing data problems, we can use the EM algorithm here. If we just dig out into this detail, you will see that actually when we calculate these Q functions in the E step, it's not that easy to calculate the expectations of ZI given YI and XI. So in that case, we use this MC, the Monte Carlo EM algorithm, to approximate this Q function. So in the Monte Carlo E step, so here we can just use the Hamiltonian Monte Carlo method. We can construct the Hamiltonian function, and then we can construct the Hamiltonian dynamic systems. Based on these dynamic systems, we can generate all these samples, which follows the ZI as the conditional distribution of ZI given XI and YI. And after that, if we have all these samples of ZIG, and we can just calculate the approximated Q function here. So this is the Monte Carlo E step. And after that, in the M step, we can just use the manifold based gradient descent method. We call the PARM algorithm to update all these parameters of interest. And we can just do all these optimization problem to get the update for the individual transformations and also the nuisance parameter sigma. And for the inference steps, we are interested to do some hypothesis testing because we want to test the relationship between the pre-ship response and some queries of interest. So in that case, we can build up these hypothesis testing problems. And so we can the straightforward way is we can construct this wild test statistics And it can be shown that this test statistics is asymptotically chi-square distribution. And in practice, we can use some parametric bootstrapping procedures to calculate the empirical distribution on the null hypothesis, which means we can calculate the p-values approximately. Okay. And next, we want to give some simulation studies and real data analysis. So all the data we are interested here is from the ADNI study. So I don't want to spend too much time here. Let me see how much time I have. Oh, I almost out of time. I just quickly go through this part. So this is so for the ADNI data. So actually, we are interested in this 2D corpus callosum contour data. And then we just use a free surfer to pre-process each T1 weighted MRI. And then we just do some quality control procedures and to remove some bad cases. And after that, we use a CC-SAG, which is a software to extract this contour information of the CC as a sagittal view on the middle sagittal slice. And after that, we have 50 landmarks in total for each CC contours. And in total, we have 409 subjects from after we do this imaging pre-processing. And this is the demographic information for all these subjects. And for the simulation study, we want to mimic our simulated data more to these real data sets. So in that case, first we feed our GeoFarm model to the CC contour data and with some predictors also from the real data, like the gender and the normalized age for all the normal controls in the ADNI1. And after that, we use obtained parameter estimators of this mu, B, and lambda and sigma as their true values. So here for each data set, we set the sample size is 100 and we choose and we fix because we have the factor model in our factor analysis framework in our model, we set the number of factors is q equal to 2. And for xi1 and xi2, we generate from the Bernoulli distribution and the uniform distribution according to their data types. And for the individual rotations, we just, instead of generate these rotations, we only need to generate these rotation angles in this orthogonal matrix. And for these rotation angles, we generate from this uniform distribution from the negative psi bar to this psi bar. And here the psi bar can be choose multiple values. Here we want to just see different scenarios to see the performance of our model. And after that, we can generate this FYI star GI from the remaining normal distribution. And for each simulation scenarios, we simulated 50 different data sets here. And this is the simulation results compared to two different methods. One is the multivariate general linear model on the manifold space, which is proposed by Kim and Muchong in the 2014 CVPR paper. And another one is MRGE, the multivariate regression model with growth errors in the remaining space, which is a method proposed in the 2018 IEEE PAMI paper. And you can see that based on this kind of the median square, sum of square, the geodesic error, and all the other forbidden normals, or the geodesic distance, you can see that our method outperforms the other two methods in all the three different index. And if we take the last picture here, which is we want to compare the estimation accuracy of these individual rotations, you will see that our method has a very good estimation accuracy in estimation this individual rotation matrix. And also, as we see that sometimes these pre-alignments may be related to these predictors like the clinical variables. So in that case, So here we also generate these individual rotations with these rotation angles related to the xi1. And after that, we compared our method with this pre-alignment-based geodesic regression model. And you will see that because the pre-alignments is related to these predictors, our method has better performance than the pre-aligned based geodesic regression model. And here is we want to investigate in the sensitivities to the choice of the number of latent factors in our factor model. And you will see that when there is no there is no latent factors in this model, and the estimation is worse than the case we have some latent factors in our GRFARM model. And another thing you can see that, so if we just misspecify the number of these latent factors, the performance doesn't change a lot, which means that actually our GRFARM is robust with respect to the choice of the latent factors, the number of latent factors. And for the real data analysis, we didn't do too much interpretations here, and we just fit our model to this real data. And also we just do the hypothesis testing problem here. You can see that we found that we include the gender, age, and the diagnosis status and the interaction term age times the diagnosis terms here. And we found that both the diagnosis status and the interaction terms has a strong relationship to these pre-shaped responses. And some take-home message. So I don't want to put too much words here. I think this picture is really good enough to send some take-home message. So you can just get all the important information of our GRFARM from this picture. And for some future work, actually, I think we need some more data sets and more comprehensive analysis for the real data analysis. And also, in this talk, I only talk about the GRFARM for the 2D objects. Actually, it can be extended to the pre-shapes from the 3D objects as a hippocampal surface. And also, we want to make our model adaptive to different kind of shape representation spaces. And now it can work for the candles and shape space. I believe that it can also work for some other popular shape space here. And the next work we are working on is the mixture geodesic regression model for the shape clustering analysis. We want to extend our model to a mixture regression model, which can be used for the clustering analysis. And the last one is the joint work with Anuj. We are working on the shape-on-shape regression model. So this is all the future work. And thank you all for your time. And yeah, I'm the last speaker. So if you have some time, if you have some questions, we can move to the discussion, floor discussion.